You ready to start?
Sure.
Lovely. Thank you very much.
I hope my screen is clear and you can hear me okay.
Yes, thank you.
Right. Do you want me to kick off? Sorry.
Yes, please.
Okay.
Start whenever you're ready, okay?
Okay. Thank you. Thank you, Mr. Chairman, for that introduction. It's a great pleasure to be here and talk to you with regard to this slightly strange title, The Nexus of Materials, Energy, and Sustainability for a Net Zero Future. I thought it was appropriate because we've got three great CDTs taking part in this particular conference. And I thought I'll do something that is hopefully thought-provoking for all of you. So I'm trying to capture something that will excite and provoke questions and thoughts as we go along. Before I forget, I'd like to thank my group that has contributed to the presentation slides that are highlighted within this talk, and also the various organizations that have paid for the research to be done. So the whole area of materials, energy, and sustainability is something at present we really just cannot forget or even allow to be given second fiddle, because everywhere we look, there is some reminder associated with the importance of materials, energy, and sustainability if we are to achieve a net zero future. Just yesterday, looking at the headlines, the IPCC, that's the Intergovernmental Panel on Climate Change, warned that we've come to the point of now or never. Now, there have been many such dire warnings previously that have indicated that unless we do something, we will go beyond a particular turning point in terms of being able to control greenhouse gas emissions and climate change as a result. But the warning is absolutely dire. And at present, it's indicated that even if we cut all the various gas emissions that have been promised by the various governments, by the turn of the century, we will have an increase of 3.2 degrees from pre-industrialization. Now, it isn't too long ago that Theresa May stood on number 10 Downing Street and indicated that the UK will enshrine within its laws the commitment to become 2050. And in that same sort of vein went on to say that our seas and our environment is being polluted by huge amounts of plastic, and these plastics that are not biodegradable go into the oceans, and that creates huge mountains of islands of non-degradable plastics. Now, we need to do something to make the world more sustainable. And it's nothing like starting with the next generation of leaders, scientists, policymakers, such as those found in CDTs, to promote this particular aspect. Now, if you think of where the world is moving towards, it's moving towards a world that is going to be controlled via the Internet of Things. It's predicted that you'll have billions and trillions of these Internet of Things connected devices that control our lives, from the point of view of simple Bluetooth connections or Zigbee connections or LoRa connections in households, to hospitals, to industrial activities. Now, if this is really going to be the case, the whole technology that is going to be used in order to make these chips, make these devices, will have to have a complete revolution in terms of the cost. And if we were to just look at the predictions in 2020 for the Internet of Things, just predicted that there would be up to 50 billion of such devices by 2025, which is just 2.5 years away. And what this means is that you would probably have over 10 IoT connected devices. Now, for most of you sitting in the room, you probably have a watch, you probably have a computer, a phone, iPad that is connected to the internet, but not much more. But the prediction is within 2.5 years, everyone on this earth will have up to 8 links to the IoT. So what this means is there must be a route to moving into this sort of world while hopefully maintaining a sustainable ecosystem. And what I'd like to show you and talk to you about is a path where we can potentially use this non-biodegradable plastics into some plastics that can potentially become electronically active, biodegradable, and also help in the sustainability of our world. Now, another link that I thought is very useful to highlight at the start of this presentation is the link that we have with electrical power. Now, it is very interesting that if we look at the total energy sector within the UK, the use of energy within the UK is roughly broken down into 3 segments. A third of the total energy use in the UK goes for residential purposes. A third goes for industrial purposes, and roughly a third, maybe 30%, goes for the transportation sector. Now, one route in which we are trying to decarbonize the world is to go into electricity, simply because electrical power is probably the most versatile in terms of being able to cater for all of these needs of society. And it also links very nicely with the theme of this conference, where you've got photovoltaics that can potentially produce your electricity through the new and sustainable photovoltaic center. Photovoltaics cannot operate on its own without having suitable storage, so the energy storage and application center, and the infrastructure has to be there in order to take the energy that has been harvested through the solar, stored through your storage, and distributed in order for the world and society to be able to utilize that power. So let me just say a few words of where I come from, and then it links to some of the research that I'm going to highlight to you. I'm the director of the Advanced Technology Institute at the University of Surrey. We've got about 150 researchers looking at different forms of nanoscale design of materials that can target some of the energy needs of the country. Within the university, we also build our own satellites through Surrey Satellite Technology Limited, and some of our work was awarded a Queen's Anniversary Prize. An area that we also got some notice in is at the Winter Olympics, where the darkest building on Earth was the Hyundai Pavilion. And this building was covered with carbon nanotubes. The carbon nanotubes actually came from a spin out from this institute called Surrey Nanosystems. And this allowed us to create the darkest building by having the most absorbent material covering the facades, outer facades of the Hyundai Pavilion. So in terms of the contents of what I want to talk to you about, I've introduced to you the nexus of materials, energy, and sustainability, and how that is really key to going towards a net zero. There are many, many reminders clear and present at now in terms of why we need to take this seriously and put more effort into it. But despite all of that, we do seem to be moving away from a more sustainable society than closer to it. We know that if the world is to continue to develop in its current form, we cannot wean the energy of energy. So as a result, the only way to continue with that journey is to decarbonize the energy that is used. The energy currently used is a terawatt problem, but when you start taking into account the millions and billions and trillions of IoT devices that also need to be connected up, it means that we need to be able to harvest energy, not just in the large terawatt scale, but also in the milliwatt scale, if we are to power all of these other devices. Solar energy is one such way in which we can harvest some of that energy. And when I use the term solar energy, it means solar energy that is used outside, but also for indoor solar, because there is no term really that has been coined in terms of energy scavenging indoors with light. And for the simplicity, it's just called indoor solar energy. So within the next 20 minutes or so, I'm going to talk about the importance really of new materials and processes as the key to a sustainable future and possibly the route to net zero. Now, if we look at the energy mix that we have at present and in the recent past, it is dominated by fossil fuels. Since Kyoto in 1997, it has been known that we need to decarbonize our energy system. We need to replace some of the fossil fuels. But even if we go back 10 years, we were typically using about 80% of fossil fuels in the form of coal, petroleum, and natural gas. And if we look closer to date, and this can be looked at in 2019 figures too, once more you add the petroleum, natural gas, and coal, you get up to this 80%. So the problem we have today in the world is that despite the need for going to renewable energies, the truly renewable part that has been developed most recently is less than 2% in terms of wind and solar. You have nuclear worldwide, which is about 5%, bioenergy that also takes into account some of the older forms of using wood and charcoal to gain energy, taking 10%. But the problem really is the fact that you still have 80% of fossil fuels. And the reason this is a problem is that those 80% of fossil fuels give out around 37 billion tons of CO2 emissions. And unfortunately, the CO2 emissions does increase. I've only shown figures up to 2018 here because due to COVID, one of the few positive things of COVID was that there was a dip from about 37 to 32 in CO2 emissions. But it is now once more rising up in its natural form. Now, the problem associated with the increase in CO2, as we all know, is that there's a linkage between the CO2 emissions and temperature around us. And until 2000, it was fairly manageable at around 1 degree. And since then, we've gone to something like 440 parts per million in CO2. And that is increasing the pressure on temperature rises, and that is giving rise to a lot of chaos around us in the form of more climatic changes, more extraordinary events. And when you have 1.5 inches of snow in Mexico, and the UK had 3 storms within 3 days just last month, it means that there is significant change happening in our ecosystem that needs to be addressed. Now, this is given rise to the fact that we really need to go to a net zero world. And the problem we currently have is that despite having routes in which to reduce CO2 emission, we still continue to have nearly 35 billion tons of CO2 emission, with only about 10 of those removed through anthropogenic means. So if we really want to have a sustainable and stable world, we need to get the balance right and move from this sort of scenario that is shown on the left-hand side to a right-hand side where you have balance. Now, this balance can only happen if we start having new decarbonized energy sources. So how do we solve this problem? Or is there a solution to it? Now, one of the factors that we certainly know is that life on Earth is sustained by the sun. And due to its current transfer of energy from solar energy to different other forms of energy, we are not just using the energy that is harvested within our fields, but we are using CO2 that has, or carbon that has been stored in the form of coal, petroleum, etc., and burning it up in minutes. So ideally, what we would really want to do is to remove the use of fossil fuels and see whether there is a route in which we can directly use sunlight to power the world. Now, is there enough energy to do that? The answer is yes. If we just look at a simple calculation and assume that the sun is a black body that is giving out radiation, we can use the black body radiation law, Planck's law, and work out the amount of power that effectively hits the world. Now, if we take a simple calculation and assume the temperature of the sun and the distance it has to travel through vacuum, you can work out that the total amount of power that effectively hits the Earth, or the energy per day, is something like 173,000 terawatts of energy. The total world use of energy at present is only about 15 terawatts. So even if you say there is half of that that's going to be reflected and another half that is unusable, you still have a 10,000 oversupply of the amount of energy that is hitting us from the sun compared to the current world use. What that effectively means is that within an hour, there is enough energy that hits the Earth that can run the world for a whole year. So the question now is, can we harness that energy? Can we harvest it usefully? One school of thought is, yes, you can do it, but the cost is too much. Now, this is something that is well worth looking at. And I wrote an editorial at the big end of last year, just before COP26 in Glasgow, that compared the levelized cost of electricity versus time for the different forms of materials that are used to generate our energy. So if we were to look at coal, for example, it's the red line shown there. And in this log plot, you can see that the levelized cost of coal for a megawatt hour is around $70 US. Now, if I compare that to nuclear, nuclear is sitting at about 90, and we know that Hinkley Point C is selling at £92.50 per megawatt hour for the next 35 years, which is the contract that the government has given. Now, if I compare that to wind and solar, which is shown down here, at present, wind and solar in large scale for a levelized field is costing around $30 US. Now, if that was looked at in terms of pounds and pence for your plug, this should be of the order of 2 cents per kilowatt hour. And we all know we pay far more than 2 cents per kilowatt hour for our electricity at present. Now, looking at the different predictions also and the different agencies that have predicted things, The prediction is that there will be a certain decrease in costs further. But the data that I have gathered shows that actually the cost of solar in particular is going to come not as drastically as in the last decade, but less so, but certainly below 2 cents per kilowatt hour. And my prediction is that by 2035, it will be so cheap that it will be better give it free rather than actually to charge it, but just charge for the connection, much like your mobile phones. Now, in terms of the area requirements, there's always been a debate as to whether there's too much area requested for solar. And what this view graph shows is the total amount of area of 20% efficient solar cells required to power the energy requirements of that particular continent. So for example, in South America, 3 of these boxes shown here would have enough power to power the whole continent. In the US, those 3 boxes would give you about 3 terawatts of energy. In Africa, again, that. So you can see from a fractional surface area point of view, it's no longer an argument. The question is whether the space that is used is going to go above arable lands or not. And we certainly have enough areas in deserts and even on waterways in which you can use floating solar. Now, if we were to wait until this is done, it will probably take some time. And some of the work that we're doing at Surrey, and I know at Sheffield with David Lindsay and Alan Dunbar, etc., is to look at next generation solar paints. So one route in which we can think about reducing the cost drastically and the materials used is by going into solution-based solar cells. So for example, instead of using 300 micron thick silicon, we can now use 100 nanometer thick polymer solar cells. Now, you immediately note that I've gone from 300 microns to 100 nanometers. There is 1,000th of the material used when we start using nanomaterials that can have equal or more absorbability associated with these structures. So the idea here is that we will make this into ink and then it will be printable. Now, we've done quite a lot of work on this, as have many other groups within the UK. We are working at pretty decent power conversion efficiencies at present when we come to scaling materials and working up. We've also seen some very new materials that come on the scene, and quite a few groups within the UK are looking at perovskite-based materials that have lowered the cost even further. Within our lab also, when we start looking at perovskite materials, for example, if you use that triple cation system of methylammonium lead iodide based systems with formamidinium and cesium on ITO, on a rigid substrate such as glass, we can get 21% with very little hysteresis associated with it. We've gone beyond that and moved from rigid to flexible. And by moving from rigid to flexible on ITO, we can lose about 1–1.5% and still get suitable efficiencies here. If we then replace your ITO with single wall carbon nanotube, I noticed there was a talk previously on using single wall nanotube as transparent conductors. So we save on using indium. We can now go to around 19% power conversion efficiency on rigid substrates and 18% on flexible substrates. But again, you notice that these are quite small areas. If we try to scale up further to 1 square centimeter, you drop another couple of percentage points on rigid and flexible. So at present, we've got a EPSRC grant between ourselves, Oxford, Cambridge, and Sheffield to look at next generation 20 square centimeter devices that are going to operate at 18 and 19% power conversion efficiency using perovskite material systems. Within these systems, there is much that we need to optimize, and we tend to start optimizing component by component, which is something that you will learn within your PhD as well as within the talks given here. So for example, if PTA as a P-type transport layer is too expensive, you will start using poly-TPD, and then you'll need to start optimizing the devices in order to examine the recombination that's taking place, the interface that is requiring better levelizing of energy levels, as well as being able to have suitable charge transport. We are also looking at scaling of these material systems. So as part of two major EU programs called Cornet and Smartronics, we are looking at next generation large scale printing of this. And typically in terms of printing, we are looking at slot die coating. So within our lab, we've just set up a roll-to-roll system that can allow us to do slot die coating of these structures. And some of our partners are looking at routes ahead, where they're looking at many kilometers of printing of these material systems. And this is typically for OPV. In the next few minutes, I'm just going to touch upon some energy storage work that we are doing, so that, again, it's to cater for the other group. So we have a number of areas where we are looking at smart batteries, novel solid state electrochemical storage systems, and an area that is certainly strong at Surrey is on the wearable and implantable devices for human-machine interface. And in one area where we are looking at on-chip micro batteries is to see whether we can produce a system that has its own measurement system onboarded. So it means that you could not just use it as a battery, but also to look at some of the chemical reactions that take place. And this is headed by Yunlong Shao, where he's looking at these tiny little batteries that allow us to change the various electrolytes that are used and monitor the performance of the device also as we change things from an in situ perspective. In terms of novel types of batteries, we are looking at lithium CO2 batteries, where here the idea being that you have the possibility of scavenging your carbon also, and while you're storing your energy, you're also able to remove some of the carbon, and that can be done also by monitoring things under a Raman system and looking at the in situ activities. We are looking at some solid state batteries using the ion beam center that is close by, that allows us to relax interface states and use ion beams in order to change the compression associated with interfaces. And finally, with regard to next generation IoT, we are looking at standard batteries that have energy scavenging and other material systems. So just to provoke more thoughts as to whether this is possible in a plastic world, we are looking at these new materials that can be solubilized, and using carbon is a great way of not just using polymers, but also using carbon nanotubes, buckyballs, and graphene. Using this, we can produce systems that are less environmentally polluting and also make materials that are pretty stable and robust. So with that, I'd like to conclude that we really do need people to start looking at new materials, new systems, particularly for energy scavenging. These systems need to be scaled up if you're starting to look at infrastructure systems that support societies. The world is likely to have over 50 billion IoT devices by 2025, and someone needs to be able to make this using sustainable processes and low energy. And solar energy certainly is one of those key areas that we need to look at in order to produce better, greener energy systems. So with that, I thank you for your attention, and I'm happy to answer any questions.
Thank you, Ravi. Have we got any questions? I think we've got time for a couple. Yeah.
You talked about new materials for various different energy applications, solar, batteries. Where do you see the most likely sort of new materials coming in and having a dramatic effect on the market? In which technology? Do you have any visions as to where the next big change is going to be?
Excellent question. You know, if I could predict it properly, I'd be a very rich man, but unfortunately I'm not. But I would say within the energy sector, I would certainly bet on solar becoming much more significant. And from a solar materials perspective, although silicon is exponentially coming down in cost, it'll always compete with the electronics, the microelectronic sector, to be able to be formed in large quantities. So therefore, there needs to be other material systems. We do know that within the organic polymer end of things and the perovskite end of things, there is much scope for much reduced costs. But again, there are problems in the stability and being able to remove the toxic elements, some toxic elements. So my feeling is that there has to be new materials that are particularly solution processable and plastic based for the energy scavenging. On storage, the lithium ion, I think, will have to change so that it has to have more energy capacity built into it. And again, if you look at aluminium and other forms, you could potentially double the energy density that you have. So it is really a new type of material that will be important in the future. So I think there is a huge amount of research that is going to be interesting in the next years to come.
Thank you very much, Ravi.
Right, hello. Thank you for your talk. So you're mentioning that, well, your prediction was by 2035, the electricity price will go down to almost zero. What will that do to the whole business model of like people building solar farms or whatever, thinking that the price is going to be somewhere and they'll be able to get their money back?
A fantastic question. And I think this is one of the reasons why I wanted to throw it in to this group of people who are thinking about sustainable infrastructure systems, etc. I think what we need to do is much like the mobile communication end of things, where it was not 10 years ago, I used to have to pay in order to get data on the internet. I used to have to pay in order to get data on my mobile phone. Nowadays, in most developed countries, it's free as long as I have a connection. So I think there has to be a complete wholesale change in the way energy is going to be sold. It also goes back to some of the talks that we've had earlier on microgrids, smart grids, where I don't think there is room for a national grid anymore. A national grid can be there as a backup, but there has to be much more localized smart grid connections available, where it's within regions that you will have your energy activities. So it's quite possible that the small farms will need to sell the energy to a particular supplier. And it's those companies such as in the mobile phone, Telefonica, Orange, all of these companies that give the connection that end up being the arbitrator on how it is monetized. So there has to be a new system that comes in, and we need to start thinking about what that could be within the next 10 years, because that's not too long to go.
Okay, thank you very much, Ravi. Right. Our next speaker will be George Wilson from the University of Sheffield. Sorry, it's different to the program.
Everyone. George, I'm a fourth year PhD student working with Dr. Becky Boston and Dr. Nick Rees-McLaren. This talk is about an ongoing project focusing on the structures that we get in sodium manganese magnesium oxide. 3 years of studying is still really hard. How this talk is going to go is I'm going to give you a quick overview of sodium cathodes, because I'm aware that a lot of you are material scientists. Then I'm going to go into what my aims are and then give you a snapshot of how that research is going. So first question, I think, is probably why sodium and why not lithium? In a word, is probably sustainability to do with the limited supply of lithium. So as more and more lithium gets extracted, the more and more expensive lithium gets, and the more and more damaging the extraction methods become to the local environment. Despite the fact that lithium performs very well and is unlikely to be replaced, and particularly in things like electric vehicles, phones, laptops, etc., if we're thinking about large scale storage where size and mass are less of an issue, then sodium in batteries, I think, provide a nice little alternative. So my work's in sodium cathodes, and they look in general like this, these like layered structures. The most important ones like being O3, P3, and P2. And this O and P denote whether the sodium ions sit in an octahedral site or a prismatic site. And the 2 and 3 refer to the number of repeating layers in the unit cell. And we'll see in a couple of slides like how that might have implications or like ramifications for its performance in a cell. In general, they have, the layered oxides have this NaXMeO2 structure, and it's this value of X that determines whether it's an octahedral or prismatic site that the sodium sits in. Because I'm worried it'll go over a lot of people's heads, I will just say that if it's a high sodium content, so like X higher than 0.9, or low, so lower than about a third, it'll be an octahedral site. And if it's at some intermediate value, like here where I've got sodium like X equals 2/3, then it'll be in a prismatic site. But during cycling, where you're continually putting sodium in and taking sodium out of the crystal structure, it will interconvert between, so O3 will convert to P3 and vice versa, and P2 will convert to O2 and vice versa. So the material that I'm working on is this sodium manganese magnesium oxide, which has there's a couple of reasons for that. One is that it's nickel and cobalt free, which is good if we're worried about sustainability. And the second, it has this high specific discharge capacity. So it's been reported that it goes up to 175 milliamp hours per gram, which is about the same level as sort of like today's lithium ion batteries. And we use this biotemplating synthesis method to generate them. So I dissolve the constituent metal ions in water, add this long chain branched polysaccharide dextran. It will coordinate, or the metals will coordinate to it, or it will coordinate to the metals, and then I dry it and then calcine it at a given temperature to generate our cathode structure. And there's a couple of benefits this has over like conventional solid state, chiefly that you have much shorter calcination time, so 2 hours versus solid state, which is about 20 hours. You also have this excellent atomic or ionic homogeneity because we've got this dissolution step, and you get very good control over particle size and morphology. So this is what they look like in the XRD, which has been talked about a couple of times. They probably look exactly the same if you've not already seen an XRD before. But the key difference here is that the P2 has these 5 big obvious peaks here between 30 and 52 thea, and the P3 has these 4 peaks, which is just an easy way of telling the difference between the two. The P2 is synthesized at 900 degrees, and the P3 is synthesized generally at 650, although in the specific XRD pattern, it's 580. So yeah, don't worry about it. So that's what they look like in the XRD. That's how we can tell we have made what we're trying to make. So here's how they perform. So this is cycling these cathodes on their own against a sodium metal anode. They're pretty stable, as you can see, so going from cycle 1, which is the black line, to cycle 10, which is the green line, the capacity doesn't change very much. It actually goes up because we're cycling against a sodium metal anode, so there's an infinite supply of sodium within the cell. But suffice it to say, it's very stable, and about 150 milliamp hours per gram, slightly lower than reported, but I'm going to chalk that up to like me needing to finesse the cell assembly slightly. So yeah, stable, which is good. Key thing to note, so this P2, reasonably smooth voltage profile. It's like not completely smooth, it's not a straight line, but it is reasonably smooth, which seems to indicate that there's not really a significant phase change going on. Compare that to the P3, which has this very long plateau, about 2.2 volts, and it's very likely to be a phase transition. So what's I think is happening, I need to confirm this with some operando XRD, is this phase transition here. So it's discharging, so you're putting sodium in. And then it's converting to this O3 phase in situ, and then converting back as you charge it. So that's how they perform separately, pretty good. But what if we were to combine them? And that's the aim of this project, is to see what happens if we can create these this biphasic material. So this is another group working on a different material containing nickel. Because it's the same material, and because the only difference between them is the calcination temperature, if you can vary that and find some midpoint, you can generate these biphasic materials which have both structures and grown next to each other. And so you get some kind of what's the word? I think not synchronicity. Well, they work together, synergy, that's the word. And so it looks like this, and this is the transmission electron microscope picture where it shows that they are like grown next to each other. So this red line is this biphasic material, outperforms these two grayed out ones, which are the materials on their own, and also outperforming this black line, which is the two powders, but then mixed together separately in the same phase ratios. So I'm going to try and do this with my material, which is what I'm going to do right now. So this is the original, this is how I would make a P3 cathode, right? So this is the acetate dextran solution. So it's got this is the dextran molecule. These are the ions coordinated to it. You dissolve it in water, dry it down, calcine at 650 degrees, and you get P3. What I'm going to do is at some point during this synthesis route, I'm going to add a pre-made P2 powder and hopefully try and get the P3 to grow around it. And so they are in contact with each other. So route 1 is add it to this aqueous solution, dry that down, calcine it, and try and get P2 and P3. The second one is to start with the acetate dextran solution, dry it, calcine it in this pre-calcination step at 300 degrees, and then mix the P2 powder into it, and then calcine at 650 degrees. So yeah, and then I will get onto a slightly different route after I explain what happened here. So route 1, I get almost entirely P3. There are some small impurities, but I don't think they're the original P2 that I started with. So what I think is happening is that somehow the P2 is getting degraded somehow in solution. It might be that the water is causing the structure to break down. Given the short time it's in contact with water, I'm not 100% sure if that's what's happening, but I will check that. What I think might be happening is that the dextran is coordinating to the P2 structure and causing it to break down slightly. So there's a couple of reasons that might be the case. I've listed here. I've run the same experiment except without the metal acetate, so just mixing P2 and dextran in water and calcining that, and we get the same result. We get a purely P3 structure. So it could be reducing atmosphere from dextran. It could be sodium impurities from dextran. I'm not sure that's the case. It could be dextran coordinating surface ions, which would be really interesting because then it means we can use dextran as an aqueous binder, similar to Sylvia's work that we talked about yesterday. And it could be that there are some structural similarities between P3 and P2 that are causing this crystal growth, which will become relevant right now. So this is the second route where we're drying it, calcining it in this pre-calcination step, and then adding the P2. So we're getting just the like sort of very well mixed metal ions in a powder growing around this P2 pre-made crystal. And we get, in this situation where I've just got the loose powder and calcining that at 650 degrees, we get a majority P2. The reason I think it's majority P2 in this XRD is because of it shows up slightly differently. The intensity counts will be slightly different in the XRD. So if I mix like two separately made powders of P3 and P2 in a 50-50 ratio by mass, it will have about this same ratio when I try and work it out using rebuild refinements. However, if I do the same, except before calcining it, I can pellet this powder and force all the different particles and stuff together, it changes the ratio of what we get out in the product. So we get this majority P3 phase. So what I think is happening is that as the P3 crystal is growing, there is some sort of interfacial interaction between the two, like the growing crystal and the P2 crystal that was already in there that's causing the P2 crystal to break down, which is quite interesting. I'd like to dig into that a little bit more. But the key thing here is that I'm not getting this one-to-one ratio that I was aiming for at the start. So I'm going to try and make this essentially in one step by finding this midpoint. That's what this next slide is. So this is using some high temperature XRD data. What I did was start with this acetate dextran solution, dry it, do this pre-calcination step because heating it up to 300 degrees is this huge volume expansion, which wouldn't do very well in a high temperature XRD. We'd get a lot of big mess everywhere. So pre-calcine it to 300 degrees, grind it up, stick it in the XRD, and then heat it from 650 degrees to 750 degrees. And then you can monitor the phase change as it heats up. So as you might expect, we've got this P3 to P2 transition. And at the midpoint, at roughly 690 degrees, which is as close as I could get, this is what it looks like. So slightly in favor of P3, but we're in the realms of about a one-to-one mixture. So what I need to do now is verify that this is the correct temperature, and I can recreate this not using the high temperature XRD furnace, which I'm not sure exactly correlates to the furnaces we've got in the lab. And then second, I need to confirm that this ratio is correct. So that's everything. These are conclusions. So this P3 to P2 formation seems to be reversible, which doesn't have any immediate uses, but I just think it's really interesting because this is meant to be like a very high temperature transition, should only happen at elevated temperatures. Not seen anyone actually reverse this transition, so it's quite interesting. Dextran might coordinate to the to the cathode structure in situ, which would be very useful if we can use it as an aqueous binder. You can favor P3 formation by having close contact with a P3 crystal, and then you can generate different P3 and P2 mixtures by tailoring the calcination temperature. So next steps is to do all that work that I said, do some TEM to see if I actually am getting these intergrowth or like biphasic structures rather than just two separately mixed powders, and then stick them in batteries and see if they actually do perform in the way that I expect them to. And at some point, I'll see if I can use Dextran as a binder. So that's everything. Thank you to all these lovely people, including my supervisors, DPSLC for funding, and everyone on the floor helped me do all the research. Does anyone have any questions?
Got any questions?
Oh, certainly. Okay, cool.
Right, okay. Our next speaker will be Tim Hutty. Sorry.
Okay, 220. Okay, so something really quite different, certainly from what we've just been talking about, and indeed from most of what we've been talking about these couple of days. So we're going to be talking about energy trading, peer-to-peer trading on a local scale. So this links back a bit to what Donovan was talking about with the vehicle to grid in his talk earlier, and also, I guess, somewhat to what Ravi was talking about in terms of smart grid localities just now. So when I say local energy trading, I'm talking on the level of a neighborhood. So we're talking households, say tens, maybe hundreds, trading energy directly with one another. So compare that to the current paradigm. You can only trade energy, whether that be fuel or electricity, with your utility supplier. Why would we want to trade with our neighbors, with our peers? A big driver of that is embedded generation, especially PV, and also electric vehicles, EVs. You've got surplus PV being generated. It's good to make use of that locally. If you've got your own car ready to charge, great. If you don't, you'd like to sell that surplus energy to your neighbor at a price that's advantageous to both of you. So the seller would like a price that's better than the grid feed-in tariff. The buyer will want a price that's less than the grid retail tariff. So PV and EVs, both drivers of this, but combined heat and power and other embedded energy technologies also. So when you're engaging with an energy market, with energy storage, there are some fairly obvious difficulties that are different from if you have dispatchable power like a gas generator, say. So you have a finite capacity of energy available to sell, or indeed to charge up. Your strategies at different times are strongly interacting, so you can only sell energy later if you've succeeded in buying it earlier. And the prices that you want to offer or ask for are not necessarily absolute, but depend on one another. So you want your sell price to be a certain function of your buy price. So there are some complexities that emerge. In terms of the literature on peer-to-peer energy trading, you don't always see energy storage included. Where you do, you often see that the work is only considered an auction mechanism over 1 hour, one time slot, or at any rate one at a time. So when the outcomes between time slots are so interdependent, it's good to try and settle the trades at all time slots at once. So there's a number of different ways we can set up power sharing or local markets. Some of these, not all of these, would be considered true peer-to-peer markets, but they're all ways you could approach incentivizing the sharing of energy locally. So central optimization, price signals, iterative price signals, and then 3 different varieties of auction. I'm not going to talk about all of those. Previously published on iterative price signals as an approach. What we're looking at in this presentation is the continuous double auction. To clarify, a double auction generally is an auction where buyers and sellers are both competing simultaneously. So the sellers need to a low enough price to undercut everyone else, and the buyers need to offer a high enough price. You can see here the demand and the supply curve. This is actually for an hour of electricity trading on the EPEX exchange. So you have all the orders to buy on the orange line arranged in descending order of price, and conversely the grey line, the orders to sell. Where those intersect, you've got a cumulative amount of energy. Obviously, this isn't local trading, this is utility scale, but it's just to illustrate. Where those intersect, all those orders to the left will be cleared, and the clearing price, you can read off the vertical axis, as £425 per megawatt hour on this occasion. Now, so that's a double auction. So you've got buyers and sellers competing. Double auction can be one-off. So everyone submits all of their bids, all of their orders to buy and sell, or it can happen on a rolling basis. So the trading on an exchange, like a stock exchange or a currency exchange, or the intraday electricity market is more in the style of a continuous double auction. Technically, there is a slight difference between a continuous double auction and true continuous trading, but the former can be considered an adequate way to study the latter. So yeah, in a continuous double auction, we repeat the double auction again and again. We continue to collect new orders to buy and sell, and we settle as many as we can as they come in. The top of the book is the outstanding orders, the best order to buy and to sell that haven't been settled yet. And yeah, as I said, this is roughly how intraday electricity markets work. And this is the approach that we've chosen to adapt for local energy trading in our work. We need to speed up a little bit. So we've built a model to simulate this. It combines any logic software, which is for it's a multi-paradigm simulation software, and we also use Pyomo to carry out optimizations. These are mixed integer linear programming optimizations. But here we've gone for a continuous double auction because in a sense, it seems like the purest, least contrived solution for trading energy. It's so to find that intersection between supply and demand curves, that's an easy job for the auctioneer. The complexity arises from deciding your strategy as the participant. This is what we tried to build. Terminology. If you hear me talk about an offer, I mean a bid to buy, or an ask, a bid to sell. These are not used consistently in the literature. Generally, I'll just try and be specific and say sell or buy. Time slot, as we've already said, so we're talking about time slots of trading through a day, so typically 24 or 48, whereas we're also going to be talking a little bit about rounds of the auction. So that is as the auction iterates and is repeated. So that's not to be confused with the time slots. This is just what a double auction looks like inside our model. So you can see that those curves of bids to buy with, should say offers to buy with descending price and sell orders with ascending price and the intersection there. So the idea is that we have one of these auctions for every time slot of a day, of an upcoming day. Potentially also a separate auction for different energy vectors. So we'd have one for heat, one for power, potentially one for gas. Obviously for heat trading, you need a network, a heat network. So I've said the strategies are based on optimization. In fact, it's a combination of optimization with some heuristic rules. Participants in the auction need to decide at any one time how much energy they want to buy or sell at each slot and what reserve price to submit. Talk about truthful or zero intelligence bidders right now, I don't think. So the optimizer specifies initially where they should buy and sell energy. They will also submit extra backup bids to buy and sell. So this means that at any one time, they potentially have on order more energy than they actually want, and equally for selling power. Now, it means that in between the settlement of each time slot, every participant gets an opportunity to cancel bids that have become superfluous or reinstate ones that have become viable. You can see top right, well, a fairly simple plot really. So in green, in blue rather, you can see the profile for an EV battery that the optimizer has planned. And in green, the one which is actually viable at that point in the trading from the deals that have been closed so far. So specifically, it should be aiming to sell a lot more energy in the second half of the day, which hopefully it will accomplish in future rounds. That's just probably should have come earlier, this slide. That's just an overview of the sort of technologies we're considering in our houses that are participating in the market. So we have the EV, the PV, essentially thermal energy storage, heat pumps. These are all included in the model. So the RSOC is a fuel cell that can work in both directions. So it can consume hydrogen to make heat and power, but it can also be used as an electrolyzer. This is as we move towards some results. This is the view from the market operator in our model. Again, midway through the auction process a day ahead. Top plot shows the clearing prices by time slot. The grey scattered points are all the prices, the red is the most recent. The next one further down is the amount of energy, electricity turned over at each time slot. So you'll see the bulges towards the beginning and the middle. I should say that zero actually zero is 5 AM on the horizontal axis. So that trading is being driven by the availability of solar power. Bottom one, you can see the amount of energy turned over cumulatively by round. You'll see the majority of trading is actually taken place within the first half dozen rounds or so. But that is a function of how often the households engage with the market and update their bids. So this is example energy flow for what we achieve with the houses engaging with the market in this way. So just for this particular study, we have PV, we have electric vehicles, which can charge bidirectionally, so they can do vehicle to grid. And we have the RSOC, which means the houses can both consume and manufacture hydrogen. So the top plot is the consumption of energy, the middle is the generation, and the bottom is a comparison of self-consumed energy in the orange with the energy which is shared in the yellow. What you'll see if you compare the top two plots is that the charging of the cars and to an extent the consumption of electricity by the electrolyzers is responding to the PV generation in the middle plot, and there's a hefty amount of energy shared if you look at plot C. This is a comparison between what happens on the left is the same plots as we just saw. On the right, if you deactivate that peer-to-peer market and just allow grid trade. Now, to say it's grid trade is a bit of a misnomer, because what's actually happening is that the houses are relying more on the fuel cells. So they plow. If you look on the top right, the houses are plowing a lot of their surplus energy into making hydrogen because they can't sell it. There's no peer-to-peer market. So if you look bottom right, you'll see no trading of energy. Now, in fact, there is a small amount because energy can be physically effectively shared without actually being traded financially. But it's not happening to nearly the same extent. So just for these 2 days, these sunny summer days, the peer-to-peer market turned over 600 kilowatt hours of energy, which resulted in the physical sharing of 527 kilowatt hours. It's not an exact correspondence, but there's always a close correlation. And on the right, as I said, the houses are relying more on the RSAC. And just for these 2 days, this was for 25 houses, if I didn't mention that, just as a test case. So they turned over nearly £80 on the peer-to-peer market. And mean household bill with peer-to-peer just across those 2 days. And this covers power and fuel, 58p, substantially less than without the peer-to-peer, £1.46. I think we need to wrap up quickly here. You can have a look at the different categories of bids that have been submitted and the prices that they achieve. So the key thing just to point out is that the flexible bids for flexible devices are achieving better prices. So the PV, which is inflexible, doesn't achieve a particularly high export price. Likewise, if you're buying power that you essentially need to travel in your EV, or for your inflexible electricity load, you're going to be paying a higher price. It's about truthful, and we haven't talked about truthful bidders, so we'll leave that. So this is work in still somewhat in development, but we can conclude that promising signs that you can save money and achieve benefits through engaging in a peer-to-peer market. Continuous double auction seems like a promising way in which to set this up. What to do? So I've said we're going to have these auctions for heat as well as power, and that work is ongoing. It's not actually too difficult a thing to add in. And we want to compare the method that we've programmed with global optimization, but also with other approaches like a time of use tariff, other auction types, such as a one-off auction, for instance, rather than continuous. And the other bit of work we're trying to push through is to compare the different bidding strategies that the participants can use. For listening, there was quite a lot in that, I think, and I've certainly missed out key things that would have probably made it easier to understand. So please do hit me with any questions.
Right. Thank you very much. We got any questions?
Yeah, thanks for the presentation. Just a general one. I'm not necessarily familiar with peer-to-peer trading. I know generally what it is, but in terms of my understanding is like you need to have a substantial amount of participants to the market to work. What do you think about that? Like you can have, I don't know, can you have peer-to-peer trading in a very small market? What do you need? Do you need 100 people, 1,000 people participating? Do you have any thoughts of that? Thank you.
So, the previous work we've done, the work has always assumed that we have some kind of microgridded setup. And so the assumption is that everyone has access to the peer-to-peer market. The question is, I think, more how many participants actually have devices that are useful. So how many people have PV, how many people have EV. In the previous work that we did using a different trading mechanism, we were looking at, I think it was 100 households. And we were seeing 10 to 20% savings on bills per year for the households. And that was kicking in, at fairly, certainly by 40% penetration of either technology. So yeah, it's, you're not looking at the built environment as it is now. You're definitely looking at a future built environment with a substantial amount of green tech. If that goes some way towards answering.
Yeah, interesting talk. I think it was on the power flow, the slides with the power flows on. It looked like you had like a significant amount more flexible demand compared to the amount that you could generate from like the self-generation. I just thought that seemed maybe a little bit overkill. Is that an efficient system? Is that a realistic system?
So I think I see what you're saying in that if you look top left at the flexible loads that have been deployed, so for the car charging in the blue and the electrolyzers in the purple, you have more deployed than is needed to absorb the PV generation in the orange. And that is true, which is why we actually see extra generation additional to the PV to meet that demand. I think the short answer to your question is no, it won't be optimal, because this isn't a top-down optimization. This is reliance on the agency of the houses who are pursuing their own goals. It will never achieve quite what a global optimizer would. I think another thing you can see going on is that sometimes undesirable bids will sneak through ahead of the more desirable ones. So what I mean by that is that someone who wants to export PV power could misguidedly ask for too high a price, and in consequence, a bid for vehicle to grid will actually get cleared ahead of that. And that means you end up with more use of the electric vehicles than is actually optimal. This is the question. It's not perfect. I think it can be refined with better price predictions and refinements and strategies.
Yeah, quite a neat concept, really. Has your model taken into account the workload involved in setting up and policing the peer-to-peer trading system? So what I guess what I'm asking is there an auction fee? So has that been taken into account?
That's a good point. No, not at this stage. It's definitely something to consider. In terms of the cost of setting this up, I guess it's smart metering initially, which a lot of people are increasingly going to have, plus some software. There is a lot of literature out there on the use of blockchain to secure transactions like this, but this work was more focused just on the flow of energy.
And then sort of a follow-on was, how do you envisage this actually happening? Is this, I mean, presumably people aren't going to sit around all day going, oh, let's bid now. Is this going to be all software driven?
So, yeah, it would certainly be automated. So we haven't talked really much about how the forecasting of the day ahead energy needs would actually be accomplished. So I guess that again touches on Donovan's talk from earlier in terms of knowing what your electric vehicle is going to be doing now. I imagine that some enthusiastic people could be persuaded to occasionally program what they expect their EV to be doing. Otherwise, it would need to be approximated by machine learning. The other thing about a continuous auction is that you can keep it open over time potentially. And so the continuous trading as time elapses can address the inaccuracies in the forecasts, which is why the intraday power markets work that way at utility scale.
Okay, right. Thank you very much. If there's no more questions. Right. Our next speaker will be Tom Entwistle from the University of Sheffield.
Yeah, this works. Does this sound working all right? Cool. So thanks for the introduction. I'm Tom. I'm here to talk to you today. Sorry. About the co-precipitation of lithium-ion batteries and specifically the nickel-rich cathodes that go into the other half of the battery. So we had Max talking earlier about the anode and the silicon that's in there. So I'm talking about the nickel-rich cathodes on the other side of the battery that help supply the lithium for that part. So yeah, my supervisor is Professor Serena Cusson, and this presentation contained a lot of her group's work, and so hopefully it'll provide a nice sort of rounded literature dive before I provide a bit of context towards what I'm specifically researching. So I'll give a bit of a background for lithium-ion batteries. They were developed in the 1980s by a group with John Goodenough in Oxfordshire, and they became commercialized in the 1990s and were really successful, but they had poor capacity. Initially, they were quite good, but they couldn't break that theoretical capacity. They couldn't get anywhere close to that theoretical capacity that they could calculate. So alternative chemistries were looked at. And one of the main candidates to sort of take over from these LCO materials were nickel, manganese, cobalt cathodes. I'll use NMC as the abbreviation from now on, just for simplicity. And these provided an increased practical capacity, so we could get high capacities, as well as maintaining some of the stabilities and some of the nice safe properties that we were looking for in the cathode materials. And it was found that although we started with this material here called NMC 111, where each nickel, cobalt, and manganese had a 1-to-1-to-1 ratio, we could increase the nickel capacity. So it was nickel 5, cobalt 2, manganese 3, up to what we were more looking for nowadays, which is nickel 8, cobalt 1, manganese 1, and above that. As we increase the nickel content, we increase the capacity. And at these sort of 8-1-1 ratios up at the top here, this will allow the commercialization of electric vehicles so they're a lot more readily available for the consumer. And so we're looking at, this presentation helps look at how to make these cathode materials so we can all buy Teslas tomorrow. So in terms of the synthesis pathway for these materials, we start off with the transition metal sulfates, the nickel, manganese, and cobalt sulfates, and those compounds. That then undergoes a sort of reaction to form a precursor. We then lithiate this and do some solid state grinding in order to mix a lithium source with these transition metal precursors before calcining them. And what we get is this nice layered structure. So you can see we've got these sort of blue octahedral shapes which contains the transition metals, and then these green dots are the lithium ions. So this nice sort of layered sandwich structure allows lithium to go in and out nice and smoothly with causing minimal disruption to the actual structure as a whole, and that allows good rate capacity so they can charge and discharge easily and at relatively high speeds. But this talk will focus on this portion of the synthesis pathway to form the precursors, because that's a lot of the chemistry, a lot of control and balance is needed to form the right particles moving forward. So yeah, with regards to this precursor synthesis, we've got the transition metal sulfates here that I've mentioned, and what we need to do with these dissolved transition metal sulfates is sort of collect them all together and form a complex. And in order to form this dissolved complex, we need a complexing agent, which in this case is ammonia. And so we use these so all the cations within the solution are all grouped together. And then when we insert this sodium hydroxide precipitating agent, they all form nice spherical particles. And then that helps improve the tap density when we form the cathodes later on as a proper slurry. And so that there's more material and higher density means that we get more energy density out at the other end. And we actually put them in cells and batteries themselves. To draw your attention to this chart on the other side, this is a Pourbaix diagram. And one of the key parameters with regards to the actual cations themselves, when complexing and precipitating, is to make sure that they are forming this hydroxide precursor state. So without going into too much chemistry, we've got the redox potential, which determines how oxidized or reduced a certain element is. And we've got the pH, which in this system determines how and when these chemicals precipitate and form these solid particles within the solution. And we're looking to sort of increase this pH to a more basic area around this sort of 10 to 15 sort of region and form this manganese or nickel hydroxide state. If we make it too oxidized, then they'll form these rogue states and have different rogue elements within this structure, which if we look onto the next slide, it will disrupt this, so it won't be as layered. It'll have lots of different blocks, which will cause them to be a bit more zigzagged, and it won't nice and neatly form these nice crystallized structure. So yeah, so I was talking about the pH just now, and that sort of helps determine at what rate it precipitates at. So it precipitates too quickly, you form lots of small and irregular particles, and it doesn't really gel very well. It doesn't really form the nice sort of desired particles that we want. It reduces the capacity, and it just they don't perform very well. The other aspect that we need to look at is the complexing agent. So if we've got too much of the complexing agent, it can go the other way, and it can cause clustering of the spherical particles, which then reduces the surface area of the particles and limits the packing ability. And then we've got the reaction time as well, which allows the spherical particles to mature more and densify as Oswald ripening occurs, and the particles sort of redissolve and reprecipitate to form nice packed spherical particles. So this is a stirred tank reactor that we've got in our lab. You can help and how much of a nightmare it is to control. But we've got a pH probe, which controls pH. We've got different feeder tubes, sure that the volume stays constant throughout. But you can, yeah, it's a lot of control, and it's taken a long time for both our group and other groups to sort of perfect this and optimize this procedure, but it does pay off. So if we look at these SEM images, so scanning sort of lesser controlled particles are rather irregular. There's some bits of clustering from imperfect some spherical particles, they're not consistent when you look compared to when you look at this bottom more optimized conditions, which are nicely controlled, and you can see they're a lot more symmetrical, a lot more uniform throughout the sample. And this is because we've optimized these conditions. So we look at pH, which is widely seen in literature as a very key parameter. We're looking at sort of 10.5 to 11.5, depending on the NMC ratio. So the nickel content within the material alters the chemistry, and we need to adapt the conditions to fit those, because otherwise you won't get these spherical particles due to the differing redox situation within the system. We need to consider the temperature, because that also affects the thermodynamic side of the redox situation. So again, that can cause oxidation of manganese, which is particularly prone to those 3+ states and form those 3+ phases, which disrupts that nice layered structure that we talked about and I showed you earlier. Just the transition metal ratios, but again, this inner atmosphere is also just required. So one of the tubes in the CSTR that I showed you in the last page is a nitrogen purge. So we put nitrogen at the bottom and let it bubble through, and that helps keep it nice and reduced to that 2+ manganese state to prevent those rogue Mn3+ and other compounds. And finally, in order to ensure that we provide enough shear forces to prevent clustering of these spherical particles, we like a nice impeller blade stirring rate. And we've got sort of optimized this at about 1,000 RPM throughout multiple literature, as well as what we've found in the lab. And this allows the particles to be mixed and break up enough so that it doesn't form too many clusters. There's maybe a couple of clusters here and there, but it's a lot more uniform across the population. So in terms of what we're looking for, in terms of what all this control means in terms of your physical product, we've got the sort of crystallography side of things and the morphology. So I think we've talked a lot about the morphology in the sense that we want a nice spherical particle to help pack them all down, improve the packing density, so when they go into the batteries that power our phones or laptops and all that, we get high energy density and more capacity out of it. But from a crystallographic point of view, we're looking for this nice structure here, this nice layered structure. So this is the precursor. So you can see there's no green lithium in here. Instead, we've got these nice hydroxide ions here. So you've got the red oxygen and the white hydrogen. What that does is provide a larger interplanar gallery. So so it allows lithium to go in when we grind it, when we calcine it, so that there's just more space for the lithium ions to intercalate during synthesis. And this is evidence in the XRD patterns, which show nice sharp peaks for this nickel precursor fingerprint. So these nice sharp peaks show that, and more layered structure because of the crystallinity of the system. Oxidation stage, which I've briefly mentioned. I'll just do a quick overview of this because this helps transition into my research, what I'm doing at the moment. We put a tube furnace, and we have an oxygen atmosphere within this tube furnace. So we've got a big oxygen tank just off the picture, and we flow oxygen through. Now, that's all well and good, but it's also a massive oxygen tank. So if something sparks, then you've got a potential safety catastrophe on your hands. Most of it's safe and it's nice and it's situated next to a window, so it's all vents out. So yeah, I think it was someone else in the Croto building that blew it up. We didn't. But yeah, we like to calcine it in this sort of conditions for about 15 to 25 hours, depending on the precise regime that they're going for. And depending on the ratio of the nickel, depends on the temperature. So lower nickel proportions is a little bit more stable because of the increased cobalt and manganese stabilizing agents. So you can have a higher temperature in order to calcine and make the final product. Whereas the higher the nickel ratio, the more unstable the nickel ions are, and therefore you need to sort of keep it at a low temperature to monitor and moderate the evolution of the nickel cations. But yeah, so it's how can we make it safer? in terms of the oxygen, but also how can we make it faster? Because if that takes a day in order to produce a lab scale, a few grams, then that's, although it has been done in industry, like how can we make it better? How can we cut it down? So this relates to my project, which involves microwaves. And due to the nature of the microwave heating, it targets the heating at a micro atomic level, as opposed to a convectional level, which targets a whole area and whole volume. So with regards to the calcination step first, so we're looking to replace oxygen with a different lithium salt and a different lithium source, that as it heats up, it degrades to form oxygen. So within the crucibles that we put into the furnaces, we've got a localized oxygen. So that's therefore less oxygen stored in the lab, and therefore it's more safe going forward. And also because of that microwave targeted heating, we reduce the calcination time. So say at the moment, this goes at 24 hours, I'm getting it down to 6 hours tops. So we can increase it fourfold. We're still to analyze the performance electrochemically and sort of optimize that side of things. But nonetheless, if we can increase the throughput fourfold, then we can produce 4 times, and then we can all buy Teslas and happy days. But yeah, and the other thing I'm looking to do is replicate what I've talked about in terms of the control within the co-precipitation to form precursor with microwave conditions. So at the moment, I've started off with solver thermal, which means just putting it in a hydrothermal bomb, so high temperature, high pressure, hope for the best. And that's starting to sort of perform more, a bit more control, but I'm hoping that we can translate this over to more conventional, widely used co-precipitation syntheses, so that we can produce same sort of particles, but in a fraction of the time, just as we've seen in the calcination step. And with that, I'd like to conclude, just to remind and emphasize about the fact that in order to produce these sensitive nickel-rich cathode materials, we need a lot of control over the reaction conditions. And in order to do that, we use co-precipitation techniques in a stirred tank reactor, or if we can make a continuous stirred tank reactor to form spherical particles that are approximately 10 micrometers in size with the secondary particles, and a high tap density of around 2 to 2.5 grams per centimeter cubed. And we're going to hopefully use that, and I'll be able to replicate these microwave environments to make them a lot faster and reduce the cost as well. I'd just like to thank the whole of Serena's group, in particular Enrique Sanchez-Perez, Nervash and Tom Isami, and Dr. Glenn Murray, as well as the CDT funding.
Questions?
That was a great talk, Tom. Will you be using for the microwave synthesis the same feedstock as the co-precipitation method in the stir tank?
I've not yet attempted the co-precipitation, so I haven't actually drawn up a proper methodology for that. I will attempt the same reactants, but at the moment for the solver thermal one, we are using different reacting agents. We're using acetates as opposed to sulfates due to the sort of thermal degradation and thermal decomposition temperatures of those materials.
Okay, but you're expecting the same sol gel kind of mechanism for the growth of the particles, for precipitation of the particles?
Hoping, yeah. There's a whole grant, so I'm just a small cog in this whole grant, so I'm hoping that I can sort of get it off to a good start. Yeah.
Thanks.
Tom, can you go back to one of your earlier slides where the y-axis was showing thermal stability? That one, yeah. So that axis then, what is that telling us? So as you're adding more nickel into it, it's becoming less thermally stable. So does that relate to Solomon's?
Yes. Yeah. So I apologize, I neglected to mention that. But as you increase the nickel content, there's less manganese and cobalt, so there's less stabilizing agents. So yes, it does become a little bit more thermally unstable, and it does reduce the temperature for thermal runaway, but it's still perceived as relatively safe. It's still, I think, let's say in excess of 200 degrees. So
again, it was just that A, that understanding, but B, the actual values there. So Solomon was saying, you know, the NMC was about 75 degrees, and then it would go into thermal runaway. So what is that thermal stability actually telling us then, that figure of 220? Say?
So that's referring to the temperature that the cathode itself degrades, as opposed to in relation to the whole cell.
All right, thank you.
Cheers.
Any more? No. All right, thank you very much. Now, finally, Alan Dunbar is going to just round up for us. So, thank you.
Okay, thank you for sticking it out to the bitter end, everyone. Not to bitter end, it's been a lot of fun. Yesterday morning, Andy opened up the conference, and he in his talk showed some images of the impacts of climate change, and Ravi alluded to similar impacts. And Andy commented that there was suggestions of hope that we could make things better. And since then, we've had a series of really interesting talks covering a really wide range of topics relevant to a wide range of regions around the world. So we touched on Tanzania, New Zealand, and obviously the UK. And those talks covered everything from energy storage, including some exploding batteries, some sustainable transport with buckling railway tracks, and there was lots of different experimental techniques thrown in there. There was modeling, using machine learning, and also density functional theory. There was experimental techniques, everything from neutron scattering to electron microscopy, and lots of other things besides. So I've really enjoyed listening to all the talks. I hope that you have as well. And one thing that I've taken away is that I think there is a real reason for hope, that with those significant challenges that are out there, that we can make a difference. So one thing I want you to take away is whenever you're spending those long hours in the lab or sat at your computer, if you're a theoretician, trying to puzzle out these tricky, difficult problems that we all face as researchers, that your work is making a difference, and that your efforts will will help to resolve some of those challenging problems that the world faces. And it's by coming together at conferences like this that we get to share what we've learned, which is really important in terms of taking that learning and making those differences and changes happen in the real world. So that's one of the messages I want you to take away from the whole experience, is that it's really important to share what you find out, and remember that it does make a difference. But these things don't happen by chance. They take a lot of time and effort, and I wanted to thank the CDTs and their various respective directors for their input, the UKRI, EPSRC for their funding to allow this event to happen. Thanks to all of you guys for attending, and as well as our online attendees across the 3 CDTs, and those of you who are from further afield, not directly linked to the CDTs, who have joined us. Thank you for your participation. Thanks to all our speakers for the fantastic talks. Without you, we wouldn't have a conference. And thanks also to the keynote speakers. Thanks to Ed for the AV, which was all very professional. I like the way that you made the last talk have a minor blip just to remind us that you're there. And finally, and by no means least, thanks to Tracy for pulling the whole thing together. So I'm going to ask Adam to come forward. Very small token of our thanks for putting the whole thing together and making my lives and the lives of everyone very, very much simpler. just to finish off, being the experimentalist that I am, I wanted to finish off with some experimental evidence. I hope that you all enjoyed the conference, and I've got some experimental evidence to suggest that at least some of you did. Thank you very much for your attendance and engagement, and have a safe journey home. And thank you for your time.